Part 15, Analyze Radar Systems. The radar module allows users to build radar system models to simulate their performance in mission scenarios and to analyze their performance. STK Radar also allows you to model an important characteristic of radar targets, the radar cross-section, in order to calculate and display, access, and to generate reports and graphs of radar system performance. Radar simulates both monostatic and bistatic radar systems and supports operations in synthetic aperture radar and search track modes. Targets may be assigned multiple frequency-dependent radar cross-sections to coincide with the various bands in operation in the scenario. We will begin by creating a new scenario. And I'm simply going to name this scenario STK Radar. In order for us to all get the same data, I'm going to change my start and stop times. I'm going to do my scenario on 1 July 2017. And I'm going to change my start time to 1600 UTCG or 1600 Zulu. This will be a 3-day long scenario, so my stop time, I can either add 3 days to the stop time, or I can simply type in plus 3 days. Once you have the start and stop time set, click OK. Now what we're going to have to do, since we're using an older date, we're going to need to bring in the archive databases of the TLEs for that time period. So frequently you're going to see me closing the Insert STK Objects tool, and I also might close the timeline view. It's up to you whether or not you want to close these, but if you have a dual screen setup, moving your Insert STK Objects tool to the other screen is probably a good idea. I don't have that to work with in this scenario, so I'm going to have to continuously open and close this tool. So I'm going to begin by saving my scenario. If you've used STK previously, you know that you want to save often. So I'm going to go up to the toolbar and click the save icon. STK will open up the Save As window. You can see that STK is going to create a folder with the same name as your scenario object, and it's going to use that file name STK Radar. All you have to do is click Save, and now every time I click Save, it's going to store my updates in a unique folder, which you always want to do when you're using STK. We'll begin by updating our satellite database. We can do that simply by coming to the object browser, opening up STK Radar, your scenario level object. I'm going to right click and select Properties. And I'm going to drop down to the basic database page. Now on this database page I can update one of 4 databases: City, Facility, Satellite, and Star. In this case, we are going to update our satellite database, so I'm just going to leave the database type set to satellite. And then I'm going to come over to the right and click on the button that says Update Database Files. Now you have 2 choices when this window opens. You can either select the Update Database option, which is going to update the database with the most current database. What we want to do, because we're using a 1 July 2017 time frame, we want to use Obtain Archive Database. So I'm going to enable the radio button for Obtain Archive Database. I can update all the databases, but in this case I'm actually just wanting to update the STK All TLE database. So I'm going to select Specific Database radio button, and it already has STK All TLE selected. And you'll notice that the archive date defaults to today's date, but that can be changed if you want to bring in even older databases into your scenario. So this is all I'm going to change. I'm simply going to click the Update button, and when the update's complete, a window will pop up and tell me that my databases have been updated. So once the information window pops up, you can click OK, and then you can close the Update Satellite Database window. Now we're not done yet. The next thing we want to do is we're going to use Terrain Server for analysis. So I'm going to come back over to the basic terrain page. And this is a little bit different than what we normally do in our training. We normally turn this off, and if we do use terrain in the training, we use a local file. However, in this scenario, we're actually going to use the terrain server. Now, your terrain server might be different than mine because I'm actually using a local terrain server that's on my machine. Chances are you're using a terrain server from the AGI headquarters. So don't worry about that. There's nothing wrong. But what we do need to do is come over to the right where it says Advanced Analysis Operations. And just to be on the safe side, I'm going to turn on all three, the terrain mask, the azimuth elevation mask, and coverage. Even though I don't think I'm going to be using them other than the azimuth elevation mask, I like to turn on all three just in case I do use them. So now we have analytical terrain running, and if you haven't used Terrain Server previously, it's bringing in both visual terrain and analytical terrain for the whole Earth. So I'm going to go down to the bottom of my GUI and click OK and select my changes. I'm going to save often. You don't have to wait for me to say save. Save whenever you can think of it. I'm going to go ahead and save. Next, we'll insert a facility that's going to act as a radar site. Now, the truth is, I could use one of three object types. I could use a facility, a place, or a target. All three are single latitude, longitude points, but in this scenario, we'll use facility. So I'm going to select facility as my object, and I'm going to come over to select a method and click on Insert Default. Click Insert. And if you look in the object browser, you'll see your facility. We're going to rename that facility. Right-click on the facility, select Rename, and I'm going to call my facility Radar Site. Radar Site. Open Radar Site's properties. You can right-click and select properties. I double-clicked. And we're going to actually change the latitude and the longitude. My latitude is going to be 30.5301. Again, 30.5301. And then if I hit my tab key, it goes down to longitude. The longitude is going to be minus 86 decimal point 2135. Again, that's minus 86 decimal point 2135. Click Apply. Next, I'm going to go back up and select the Basic ASL Mask page. Basic ASL Mask. On this page, we're going to create an ASL mask file using the terrain server terrain, and it's going to create a 360-degree field of view around that ground object. So at the top of the GUI where it says Use, you want to change that pull-down menu to Terrain Data, and also turn on Use Mask for Access Constraint. So this is a dual feature that window here. We're going to use the terrain data for our mask, and we're going to use the mask when we do accesses in our scenario. Drop down to the bottom of the GUI and click OK and accept your changes. Now you might have a slight delay. In your case, the delay is most likely coming from the fact that you're going out over the internet to the AGI server, to terrain server, and then pulling the data into your scenario. Once your GUI closes, you can save your scenario again. The next thing we're going to look at is a tool that we don't talk about except in this lesson called the Deck Access tool. Now, the access tool itself allows you to do an access from one known object to another known object or to many known objects. The beauty of the Deck Access tool allows you to do an access from a known object against a whole database of objects. So basically, I could say, all right, I have a field of view pointing in a specific direction, and I want to know during the next 24 hours which satellites are going to fly through my field of view. That's what the Deck Access tool allows me to do. We'll begin by putting a sensor object onto our radar site. So I'm going to return to the Insert STK Objects tool. And go down to Attached Objects and select Sensor. And again, I'm going to use the Insert Default method and click Insert. When the Select Object window appears, select Radar Site. That's the object we're attaching the sensor to. Then click OK. And if you look in the object browser, you'll see you have a sensor attached to your radar site. We're going to rename this sensor Radar FOV, which stands for Radar Field of View. Radar FOV. So what we're doing here is we're going to simulate the field of view of our radar site that's going to track satellites. So I'm going to explain what's going to happen here. We're going to create a rectangular sensor. We're going to point that sensor with an azimuth of 180 degrees, which means that the bore sight of the sensor itself is going to point south. And we're going to give that sensor an elevation of 50 degrees. When using the rectangular sensor, it's going to give us vertical half angles and horizontal half angles. The vertical half angle will be 50 degrees, so basically what that's going to do is give us a vertical field of view of 100 degrees, and a horizontal half angle of 60 degrees will give us a horizontal field of view of 120 degrees. Now, this kind of radar site is usually software controlled, and the truth is that in the real world, this site could see outside of that sensor's field of view. But based on the software control of the radar site, we're going to say all reporting purposes are going to take place within that field of view that we're going to build. On top of this, our radar site is going to have a range of 22,000 nautical miles, and we're going to tell that radar site to take terrain into consideration. So open the properties of Radar FOV. And we'll start on the basic definition page by changing the sensor type to a rectangular sensor. Rectangular. Change your vertical half angle to 50 degrees, 50. And then I'll just simply hit the tab key and it'll move down the horizontal half angle. Oh, it doesn't. I'm going to have to select it. Horizontal half angle, change it to 60. And click Apply. So again, I have 100 degrees vertical total and 120 degrees horizontal total. Next, we're going to point the satellite by reorienting it. So I'm going to come over to the basic pointing page. We're going to leave the pointing type at fixed, but I'm going to change the azimuth to 180 degrees, 180, and change the elevation to 50 degrees. So what you did here is you changed the bore sight of the sensor to 180. So I'm going to see 60 degrees on either side of that. And by selecting an elevation of 50 degrees, if you recall, our vertical half angle is 50. So I'm bore sighting it at 50 degrees. So I'm going to have 50 degrees from the bore sight down to the ground and another 50 degrees above the bore sight. Click Apply. And let's select the Constraints Basic page, Constraints Basic. Now, if you've used STK before, and I'm assuming you have, line of sight takes into account any analysis from horizon to horizon. With a sensor object, you also get field of view. Field of view is going to take into account only objects that are inside the field of view that you just created with your vertical half angles. We also want to turn on As-Ill Mask. So I'm going to turn that on, and what that does is it brings in the As-Ill Mask that we created for its parent object, the facility object, and applies it to the sensor object. Finally, I'm going to come up to the top to range and turn on max for range. And our system is going to report any satellites within 22,000 nautical miles inside that field of view of the sensor. So I'm going to type in 22,000 and then NM. Let me turn off my caps lock. NM. And that's going to give me a field of view of 120 degrees horizontal, 100 degrees vertical, out to 22,000 nautical miles. Click Apply. And bring your 3D graphic window to the front. And if you use your left mouse button and turn your earth around, you're going to see the sensor field of view. Now later in the scenario, when we build our radar object, I'm going to turn on the antenna pattern volume. And by having this sensor field of view so dark, it's going to be difficult to see that. So what I'm going to do is turn off the sensor. I'm not actually going to turn it off. I'm going to increase the translucency of the cone, but I'm going to leave the extents of the sensor alone. Now I can make these lines translucent also, and I'll show you where that's done, but we're only going to change the translucency of the cone itself. So let's return to the properties of radar field of view, and since I never closed them, I'm simply going to come down to the bottom and click on the tab. If you did close yours, you can just reopen the properties of radar FOV. And we're going to select the 3D graphics attributes page. 3D graphics attributes. And on the 3D graphic attributes page, you're going to see where it says projection percentage translucency. Let's change that translucency to 90%. So I'm just going to type in 90. And before I move on, I'm not going to do this, but I'm just pointing it out. If you look above that where it says lines, if we were to turn on translucent lines, it would just create lines that are translucent too. That's out at the extent of the sensor. In this case, I'm just going to leave them be because for my own situational awareness, I want to see that. There's no right or wrong here. It's totally up to you. So 90% translucency, click OK. And as you can see now in my 3D graphic window, it's almost impossible for me to see my sensor field of view, but I can see the extents. I'm going to save my scenario once again. And now we want to determine which satellites fly through the sensor field of view by using the deck access tool. Now, if we do run this for 24 hours, it would take a while. So what we'll do in this scenario is just take a 1-minute snapshot just to quickly show you how this works. So I'm going to go over to the object browser, right-click on radar field of view, radar FOV, and select deck access. Because I right-clicked on radar FOV and then opened up the deck access tool, my deck access 4 is already selected for me. What I do need to do is change my stop time for input. Now you could change it to 1 July and then make it 1601, or you could do it the way I'm going to do it. I'm simply going to type in the plus sign, the number 1, and then MIN for minutes. So you have a choice on how you want to do that. You'll notice below that it says select target deck. It defaults to satellite, and that's the target deck we're going to use. We're going to use the satellite database that we updated at the beginning of this scenario. So I'm going to come down the file and go over to the right and click on the ellipsis button. It usually defaults to the database. If for some reason you had played with this in a previous time and selected a different database, you might not have this same path. So if you look at the top of my open window, I'll leave the path there for a minute if your satellites aren't showing up to make sure that you can go to where you updated your satellites. As I'm sitting here, if you look in the list of satellites, you'll notice that out of my 4 databases are older databases, and the one I updated today, the STK alltle.tce file, is showing today's date. So I'm going to come down to the databases and select that one file, STK alltle.tce. Now, STK can read TLEs out of at least 3 databases that I know of, and they're simply ASCII text databases, and they have extensions of .tce, .tle, or .txt. So all 3 of those, if you have a custom or a classified 2-line element set in a file with one of those 3 extensions, STK will be able to use it. So I've selected STK alltle.tce. I'm going to come down and click open. And you'll see where it says type satellite file STK alltle.tce. Down at the bottom it says input sorting, and we're going to sort by start time, and the start time is up here in this field. And we're also going to create a report, which if we want to, I'm not going to actually do that. So I'm just going to leave create a report selected and simply click the button that says compute accesses. Now, we also have the choice of computing in parallel, which it would use all of your available processing power on your computer. But in this case, because it was only a 1-minute snapshot, I really didn't worry about that. But as you can see, even with a 1-minute snapshot, you have an extensive list of satellites. And if you look over on the right where it says duration, it shows how long that field of view of your sensor is tracking a satellite. You'll notice that I have a lot of satellites in here that have a 60-second time, which is the length of my report. And chances are that every one of those, well, the vast majority of them are going to be geosynchronous satellites. So again, that's a deck access tool. The deck access tool, again, allows you to point, in this case, a sensor object in a particular region, volume, I could call it, of space. Or you could do it from a satellite down to the ground if you wanted to know, for instance, what cities can I see with my satellite camera, let's say. The deck access tool allows you to do that. It's a very useful tool. So I'm going to go down. I know what satellites, if I was actually doing this in the real world, I would know what satellites my radar could potentially track at this time. I'm going to close the report. You could save it as an external file or a quick report if you required to do so. So I'm going to close that report, and I'm going to close the deck access tool by simply clicking cancel. And I'm going to save my scenario once again. Next, we're going to model a target, and then we're going to model a radar. Our target for this scenario is going to be the International Space Station due to the fact that it has a very large radar cross-section, and it's going to be easy for my radars to track it. Now, we might not track it often, but we'll be able to track it, and therefore that's why I have the stop time, or I should say the scenario analysis period, opened up for a complete 3-day period. So first thing I'll do is go into the Insert STK Objects tool, select Satellite as the object, and from Standard Object Database as the method, and click Insert. If you are using an internet connection, and most people will be when they're going through this tutorial, you might have a delay while you're waiting for that database to open because you're selecting it from the AGI server. My assumption is, again, that you've used STK, but if you haven't or you're not familiar with the TLEs, what's happening here is once a day, every 24 hours, STK downloads all the unclassified 2-line element sets from SpaceTrack. And that's what we're tapping into. So if you have in the real world a classified 2-line element set, you're going to have to create your own file and tap into that. So in this case, we're going to use the International Space Station. I'm going to use the NORAD catalog number to search for that. And as STK, it's called an SSC number. And I'm going to go up to the top, upper left-hand side where it says name or ID, and I'm going to type in 25544. 25544. Go down to the bottom of the screen and click search. So if you look at the results, you get 3 selections, but the truth is all 3 are the same. But if you look at the data source, one of them is coming from the AGI Standard Object Data Service, which is the AGI server itself, which is always probably the smartest way to bring in your TLEs if you're using space track TLEs from us, because you're always going to get the most up-to-date TLE. And also, even though we updated our databases, which in this case we could actually use a local database in this case because it's pulling from the STK all-TLE .tce database. By using the AGI Standard Object Data Service, if we hadn't used the deck access tool in this scenario, we could have just gone straight to bringing in the ISS for this time period, and STK would have shipped this ISS to your scenario with all the required TLEs based on your start and stop time. You wouldn't have had to update your databases. We had to update our databases in order to use the deck access tool to get correct data for this time period. So I'm going to go ahead and use the first one, the common name ISS ARIA. It's up to you if you want to change the color. That's simply going to apply a color against your label and your ephemeris, and then click Insert. It's going to download that satellite and propagate it using the SGP4 propagator. Once you see your satellite in the object browser, you can close the Search Standard Object Data window and save your scenario. A question often asked in my class is when you look at the ISS's in the 3D graphic window, if you look at its ephemeris, you'll notice that there's one that's in orbit, but there's also one along the ground, and then there's a split on the ground. And that's simply due to it showing what the track's going to look like on the ground as the satellite orbits. And as it finally comes around to the end of that particular orbit, that space between these 2 points is how much the Earth rotated. There's nothing wrong. So let's open the properties for the International Space Station. So I'm going to come over to the object browser, right-click on the ISS and select Properties. And before I move on, I do want to show you what's going on here as far as TLEs are concerned. So in this TLE source field, click the button that says Preview. You'll notice that the ISS was brought in when it propagated it using multiple TLEs. And what that ensures is when you're doing your analysis with this satellite for 3 days, STK will automatically tap into the correct TLE for that specific time period. And that's important if, for instance, they did some sort of station keeping or they actually move a satellite, for instance. It's important to have all those TLEs. So I'm going to go down to the bottom of the TLE preview window and click Close. And now what we're going to do is we're going to create a radar cross-section. So I'm going to come back over here and scroll down to the bottom of the list. Find the RF radar cross-section page. RF radar cross-section. Up at the top, you're going to see a checkbox for Inherit. Turn that off. What that means is you can also set a constant RCS value at the scenario level, and whatever those values are would be brought in for all objects in STK. I could have done that, but I'm going to build an RCS specific to the International Space Station myself for this one particular object. I'm going to begin by changing the swirling case. So I'm going to come down to where it says swirling case and change it to a case 4. Swirling is an individual that came up with different algorithms for different reflective surfaces. A swirling case 4 probability density function approximates an object with one large scattering surface with several other small scattering surfaces. So basically I'm just saying the ISS has a couple large modules on it, and then there's a lot of antennas, there's solar panels, that kind of thing. Next is compute type. Now you'll notice it defaults to constant value, and we are going to use constant value, but I do want to point a couple things out here. One of the things that many people will use when they're doing this in STK is if they want to make it as realistic as possible, they use what's called an external file, and it's nothing other than an RCS file. So different targets out there, aircraft, for instance, satellites, have their own RCS file and the signature, and that would give you more of a realistic scenario because the object flying straight towards you would give you one type of reflection. From the side, it would give you another reflection. From the rear, it would give you a different reflection flying straight overhead, so on and so forth. Well, we don't have an RCS file, so what we're going to use is a constant value, but we can give our satellite a realistic constant RCS value. Now, if you go over to the right of this field, you're going to notice a small pull-down menu. When I click it, it opens up. Throughout STK, you're going to see these little pull-down menus, and they show you the different units that can be used in these different fields. So it defaults to dB squared meters, but what we're going to do is change it to squared meters. The International Space Station has a value of 402 squared meters. 402. If you go down to the apply key and click that, you'll notice that STK is going to set the equivalent of the default unit, which comes out to be 26, I'll just say 26 dBSM. So now we have a realistic radar cross section. Click OK and save. Again, when you're using STK, save often. Next, we're going to insert a radar, and to make this quick and easy in this particular scenario, we're going to build the radar somewhat to specifications, but what we're going to do is to make it easy and quick, we're going to load the radar site and we're going to attach it as a child of the sensor, and we're going to use the sensor's field of view during our analysis. And what that will do is the radar site that we build, which is going to be a phased array radar, will only report satellites that it sees inside that sensor field of view, even though it can see satellites outside that sensor field of view. So that's just one way of doing it. As far as realism is concerned, you would probably build the radar to specifications completely and just use those specifications. But the way I'm going to do it works too. So I'm going to go ahead and go back into the Insert STK Objects tool. Select Radar as the object. Insert Default as the method. And click Insert. When the Select Object window appears, select Radar FOV, Radar Field of View, and click OK. And so you're attaching the radar object to the sensor object, which you can see in the object browser. Let's rename that radar. I'm going to call that radar ISS Tracker, as in International Space Station Tracker. ISS Tracker. Open the properties for ISS Tracker. So the radar object in STK can either be monostatic or bistatic. We're going to use a monostatic, and that simply means this site transmits and receives. We are going to use a search track type. And again, we're not going to get into theory or anything here. We're just going to use some standard basic settings for this particular radar site. So one of the things that we do want to set is a fixed pulse number. So I'm going to come down to where it says probability, or I'm sorry, pulse integration tab, and select that. And right now it says goal SNR. Open up that pull down menu and change it to fixed pulse number, and change that pulse number to 8. So there's a lot of people in the world that can listen to a radar system through their headsets and determine what that system is. based on certain sounds the radar system makes. And in this case, this radar system might be detectable. One of the ways would be by its pulse number. Click Apply. So let's begin by selecting Pulse Integration tab. I just want to make sure that you have your pulse number of 8. And then we're going to create our antenna. So I'm going to select the Antenna tab. And on the Model Specs tab where it says Type, I'm going to change the type to Phased Array. As you can see, STK has multiple antenna types. We're going to use Phased Array. So I'm going to select Phased Array, click OK. Next, the assumption would be that this phased array system could be upwards of over 1,000 elements. But I'm not going to use the complete system to track one target. So what I'm going to do is somewhat cheat in here, and I'm going to just put in the amount of elements that I'm going to use to track the International Space Station. So I'm going to come down to number of elements, and I'm going to change the X and Y to 7. And when I apply that, what that does is it gives me 37 elements. Next, I'm going to select the tab that says Beam Direction Provider. So you can make it either fixed and orient the system, or you can orient it the way we did, but we can also tell the elements that they can track the ISS. Now, because the way I set this up, this system, if I didn't give it limitations, could track 360 degrees in any direction. But by attaching the sensor or the radar site to the sensor, even though I can still track in all directions, only objects that I see in the field of view of the sensor will be reported. So I'm going to come down to where it says Beam Steering and turn on Enabled. Now, here's where, if you were doing this without the sensor, you might have to set up your azimuth steering and your elevation steering for your elements. But I'm bypassing that because I'm making it as simple by using the sensor itself. But I am going to come down to the bottom and select ISS Zarya and move it over to the right, and I'm going to track the ISS. So the thing here is what I'm saying is anytime the ISS is inside the field of view of my sensor, those elements can track it. Now, this is not in this scenario, but it's of interest to a lot of people. Go ahead and click Apply and select the Null Direction Provider. And if you were experiencing, let's say you had a potential interference source out there of some sort, you could turn on nulls and you could tell it, STK, which object you want to point your nulls at. Maybe it will decrease the interference, maybe it won't. It just depends on the object, it depends on how you have your system set up. So next thing I will do is we're going to constrain this after we create our transmitter. So let's go up and select transmitter. We will use wavelength. I'm going to change the wavelength to 68 centimeters. So I'm going to type in 68 cm. And the power of my system is going to be 370 kilowatts. Now, the reason for 370 is each antenna element receives power from a separate transmitter module that has an output power of 10 kilowatts. We have 37 elements, therefore 370 kilowatts. So you can open up the pull down menu and select KW. Sometimes in these fields, case does matter, so the safe way to do it, unless you're using it all the time, is to just go ahead and open up that pull down menu. And we're going to change this value to 370. Click Apply and it'll put all the units back to their defaults. Next, we'll select the Receiver tab. And I'm just going to say that the system specs says that the low noise amplifier has a 20 dB gain, which simulates the post-pulse compression gain. So where you see LNA gain, change that value to 20 dB and click apply. So now we have the parameters of our system set up. There's a lot more we could have done, but we'll stop at that point. Now I will drop down to the Constraints Basic page. And there's two things in the Constraints Basic page that are important. We want to turn on the field of view, which is going to take into account the field of view of its parent, which is a sensor. Therefore, now when I do any type of analyses with this radar site, it will only report objects that are inside the field of view of its parent. And I'm also going to turn on Azle Mask, and that's going to apply the Azle Mask file that we created for the facility object that got passed down to the sensor object to the radar object. It's a lot, but that's how it works. Next, I might want to view my antenna pattern. Now, any antenna in STK, you can do what I'm getting ready to show you. I just happen to be doing it with the phased array radar on my, or the phased array antenna on my radar site. So let's click apply. Save your scenario. This is going to be graphic intensive for your computer, depending on what kind of graphics card you have. And we're going to go to the 3D Graphic Attributes page. 3D Graphic Attributes. On the 3D Graphic Attributes page, where it says Volume Graphics, turn on Show Volume. To give your graphics card somewhat of a break, I'm going to turn on Show as Wireframe. Set your scale dB to 1 kilometer, 1. Gain scale per dB, 1 kilometer. And the gain offset, I'm going to set that to 10 dB. So this combination, the gain scale per dB, is going to show me different colors based on the gain. Each change is going to be a different color a kilometer at a time. And the gain offset at 10 dB is going to give me a better view of all my side lobes. I'm going to drop down to where it says Set Azimuth and Elevation Resolution together and turn that on. That simply means that whatever resolution I set for azimuth will automatically be applied to elevation. I'm going to change my resolution to 0.5. The lower your resolution, the more points, and therefore the nicer your antenna pattern will look in your 3D graphic window. So click OK. Save your scenario. And go down to the object browser, right-click on Radar Site, and select Zoom to. So looks very 1960s, but if you start to scroll out, what you're going to see is your antenna pattern for this phased array system. Obviously, if I had more elements, I would see more side lobes. The maximum gain is right down the middle of this system, and red is where the most power is, and violet is where your least amount of power is. And again, this doesn't mean anything, it's purely visual, but this allows you to look at the antenna pattern of the antenna that you're using in STK. The next thing I'm going to do is see if I can track the International Space Station. So I'm going to come over to the object browser, right-click on the ISS, and select the Access tool, Access. By right-clicking on the ISS in the object browser, my Access 4 is already set up, and whatever you have in Access 4 is where you're looking from. So I'm actually doing this backwards. I'm looking from the ISS to the radar, but I could have done it the other way, the radar to the ISS. It really doesn't matter. I'm going to go in the associated objects list here and expand radar site, and then I'm going to expand the sensor and select ISS Tracker. Come over to the right where it says Reports, and at the bottom of that Reports field, click on the button that says Report and Graph Manager. Report and Graph Manager. So when this opens, you'll see underneath the object type window that your ISS Tracker is selected, and this key here means it's an access. Then I'm going to come over to the styles window, and what we're going to do is we're going to create a custom graph that shows the integrated probability of detection and the probability of detection. I'm using integrated because we turned on the pulse number, and I want to see that, and at times your integrated values might look different than just the standard probability of detection. So on the My Styles folder that you'll see in the list here, right click on My Styles, select New, and then select Graph. Now before I move on, look at what you have here. You're going to rename this graph, but notice that you're currently in the rename mode. After we name the graph, I'm still going to be in the rename mode. At that time, I will click my Enter key on my keyboard, and what that will do is automatically take me to the properties. So I'm going to rename this graph PDET, P-D-E-T, for probability of detection. I'm still in rename mode. And then click the Enter key. And as I said, that takes me to the properties. The key to making a custom report or a custom graph in STK is that you're going to have to know where to find your data providers, and there's a lot. So in this case, for a radar system, chances are I'm looking for something out of the data provider called Radar Search Track. Radar Search Track. When you find Radar Search Track, expand that. And so we want two. The first one I'm going to bring over into the y-axis list is the ST integrated PDET. ST integrated PDET. And I'm going to move that into the y-axis field. Then I'm going to come back over and I'm going to select the ST PDET1 and move that into the y2 axis field. Now I could have moved them both into the y-axis field, but in this case I want to just have each one of them in its own axis. That's just a personal thing. So I have my ST integrated PDET in my y-axis and my ST PDET in my y2 axis, and then I'm going to click OK. So now I have a custom graph that I built. I'm going to come into the styles list, select my graph called PDET, and generate that graph. So as you can see on this particular date, at the very beginning of the graph and at the very end of the graph, I have some very strong returns from the International Space Station. Now, the first return at the beginning, the ST PDET or integrated PDET is what I see, but there's a good chance that the ST PDET1's inside there. If I zoom in, and by the way, a graph in STK, the zoom in function is automatically turned on. If I zoom into that, it kind of breaks it down a little bit, makes it a little easier for me to see both of those graphs. Now, what we're looking for is a PDET above 0.5. Anything above 0.5 means I have a very good, very high probability that I'm tracking that object. I'm going to go up to the top of the graph and click the zoom out icon, and I'm going to go over to the right and zoom into this one all the way over on the right and look at this one. And again, you can see my integrated PDET and my PDET, and both of these are well over 5, and so I can track satellite here. Now, it doesn't mean that I can't see it at other times. It's just that the radar system, as far as tracking is concerned, the probability of detection is very low. So if I zoom back out again and look, you can see that I have some other areas here where the tracking is very low. This one pops up a little bit better. So I see it multiple times, but the probability of detection of 0.5 or better is on the beginning of the graph and at the end of the graph. So I hope this gives you a good introduction to the radar object in STK and the phased array antenna. And that is the end of the scenario.